So our next speaker is Jeff Siegel from the University of Toronto. And this morning, those of you who were at the plenary lecture heard about the importance of moisture, and Jeff is going to try to go into some detail on the relevance of moisture.
All right, can everyone hear me? Okay. So if we think about the evolution that we just saw in terms of microbiology, I'm like the single-celled organism all the way over to the left. But what I do care about is buildings. And what I want to talk about today is particularly moisture in buildings. And the way I'm kind of framing things today is, first I want to make an overall justification for why moisture is so important to our discussion of the indoor microbiome. And then I want to talk both a little bit from a research perspective, but mostly from a practical perspective of how do we assess and why should we assess moisture in buildings. So this is a picture that I've shown many, many times. Of course, there's many, many things we should care about in understanding the conditions that lead to that affect the indoor microbiome. Many, many things. And if we kind of look at this more fundamentally, there are really three things that we should be thinking about. We should be thinking about the environmental conditions, the food that's available for microorganisms, and we should be thinking about water and moisture. So first on environmental conditions. If you look on indoor surfaces, and again, keeping this for a second, indoor surfaces, you tend to see, compared to outdoors, the big difference is going from indoors to outdoors. You see relatively small ranges of things like temperature and light on indoor surfaces. But the real issue, the real reason why I'm going to focus on moisture is we don't really have a lot of good data on the environmental conditions that we would really need to understand the indoor microbiome. So things like surface pH. We have very, very little data indoors. Really relevant temperatures. We, of course, have a lot of air temperature measurements in buildings, but we have many, many fewer surface temperature measurements, and we have even fewer things like radiative or operative temperature measurements, which might be relevant for microbial growth. Again, with light, we have a lot of measure of illumination on surfaces, but relatively little spectral data that really would let us evaluate some strong hypotheses. So generally, we have not very much data on environmental conditions, and that gets much worse when you go into interstitial spaces like Mia talked about this morning. Food isn't worth talking about because there's lots of food everywhere for microorganisms inside. So that's generally not a limiting factor. And that kind of brings us to water. And when I think about water, I think about kind of some of the practicality of how we measure moisture in buildings. So if we start with the very practical, you can just look for evidence of staining in many materials. So this is, in fact, a picture of the ceiling of my office. And there is an environmental lab above my office. And every few months or so, there's something that happens, probably with wastewater in that lab. And this is what my ceiling looks like. And I send the building manager the Mark Mendel's article that says that moisture damage is associated with health problems, and my ceiling tiles get replaced, and it happens again. But that's a very practical way. If there's water, we know there's a problem. And by the way, it might not be microbiological, it might be chemical for all we know, but moisture is a problem. But if we go to the extreme other end of the scale, there's some really compelling research that's been done for many years here here in Eindhoven by Olaf Adam, where you look at a parameter called water activity. And he uses nuclear magnetic resonance imaging to look very, very detailed at moisture and moisture transport and its association with fungal growth in building materials. Now, the problem with that is that's lab-based research. It's very hard to do that in situ in buildings, but I think it offers us a lot of mechanistic understanding. So actually in buildings, probably the most common way that we assess moisture is with a pin moisture meter, like you see here. And this is basically a device with a couple of pins. You stick it in material, and it's nominally calibrated to some sort of wood usually, and it tells you the moisture content. I'll talk a little bit more about those devices in a little bit. And that's nice, but it gives you a single point measurement. Or maybe it's not nice, but in any case, it gives you a single point measurement. So what people tend to do a lot of is measure humidity. And Jordan mentioned this, you can, there are many, many humidity sensors available. They measure relative humidity. Many of them can data log for long periods of time. And we can get a sense of how much moisture is in the air. And where I think we might be going is in a measurement more like this, which is equilibrium relative humidity. It's a relative humidity sensor in a sealed headspace. So you attach that black suction cup ring to a surface, and you measure the humidity in the headspace. And that gives you an air relative humidity measurement, but it's much more coupled to the material. And I'll talk more about that as well. And just because some of these measurements may not be familiar to everyone in the room, this is just kind of a cartoon schematic, just so that we're looking at these things together. On the air side, we have the air relative humidity, or occasionally other parameters that measure the amount of moisture in the air. On the material side, we have typically the moisture content, how much moisture is in the material. What we actually care about from a biological perspective is this water activity, which is, kind of think of it as available water at the surface where the microorganism is. And then we have some of these surrogate measures, what I call equilibrium relative humidity, other people call other things, which is basically just in a sealed headspace above the surface. So those are the moisture measurements I'm gonna talk about today. And some comments here is, if buildings weren't so complicated, it would be really simple, because at all of the measurements of relative humidity, water activity you see here, at equilibrium, they're all the same. The problem is buildings are never at equilibrium. They're very, very dynamic, and that really complicates how we look at moisture. So if what you're interested in is health, probably what you're most interested in is there moisture damage or not? And looking at staining is great. The problem with it is, of course, there's lots of materials that don't stain. There's lots of places in a building that aren't visible to us. So even if there is moisture damage, so it's not really a very robust way of actually looking at moisture. Pin moisture meters make that a little bit better. My challenge with, or the challenge that I see with pin moisture meters is that they're one of those things that you really have to understand well to get good data from. They have a lot of limitations. The electrical contact that those pins make with the material, how they're calibrated, with what spatial distribution you have to do measurements, all matter a lot. So I tend to kind of, I think they have value in the right hands as a diagnostic tool, but they don't really tell us a whole lot about moisture indoors. So given that what we really want to know is at the opposite end of the spectrum, this water activity, one of the reasons we want to know it is we can calculate something that has been around for a while, relatively new to me, but an interesting concept here called the time of wetness. And the idea of the time of wetness is the amount of time that a microorganism experiences water activity above a threshold. So just to show that visually for a second, if we have water activity as a function of time in a building here, and let's say we have a microorganism that requires a water activity of 0.7 to proliferate. So the time of wetness here is the amount of time that the trace is above 0.7, shown there by the arrow at the bottom. If instead we have a different microorganism that requires a water activity of 0.8 to proliferate, it's going to have a shorter time of wetness. And I like this time of wetness concept for a lot of reasons, but one of it is it gets at the dimension of, it gets at how long things are staying wet. And that's gonna be important in a second. The problem is, of course, as I said, water activity is really difficult to measure in situ in buildings. In fact, I was going to say impossible there, but I'm sure someone has done it. I just haven't found it anywhere or found any easy way to do it. And so the fact that we have, that's what we really want to know means we have to find some surrogates. So what a lot of people are doing is using relative humidity as a surrogate for water activity. And the comment I'd make about relative humidity is that, to my knowledge, no one has ever causally associated moisture in the air with any kind of microbial growth or proliferation. So microbes, as far as I know, are not pulling moisture molecules out of the air. At least I haven't seen any evidence of that anywhere. And so what a lot of people do, at least in a practical sense, is use relative humidity to look at condensation potential. So for example, you look at when the relative humidity, you measure relative humidity, if you see it go above 70% for many people or 80% for some people, then you've got a problem and you fix your building design. But I'm going to suggest a lot of caution here, because a lot of materials in buildings can get wet and be just fine, especially if they're not wet for that long. So a short excursion above your threshold relative humidity is probably not a big deal. And some materials can tolerate quite high relative humidities for a long period of time. So what that pushes me towards is this idea of equilibrium relative humidity. Is this a better measure? So the basic argument that I and others make about why we think equilibrium relative humidity is more microbially relevant is, first of all, air relative humidity, for instance, in this room, is only weakly affected by the materials in this room. It's affected by a lot of other things much more strongly. But generally speaking, whether we're talking about inside surfaces or interstitial surfaces or outdoor surfaces, microorganisms proliferate on those surfaces. And so if you make this equilibrium relative humidity measurement where you're coupled very strongly to the material, then you start to see the material properties, so things like the porosity and the hydrophilicity are very important. So those of you who know me know I like to make measurements for long period of time in buildings, years, if I can get away with it. And so this is a measurement. This is in an office in Toronto. This is just one day to not be overwhelming here. The black trace in the middle there is the air relative humidity, and the other colors are 3 different building materials, the equilibrium relative humidity above those materials. And there are a couple of things that I want you to note. First of all, there's a lag between when the relative humidity changes and the equilibrium relative humidity change, and that lag is material specific and typically varies over the course of hours. The second comment I want to make here, and is the more important one, is that there is really a big difference between relative humidity and equilibrium relative humidity for some materials. So this is not a particularly extreme day, but note that you can kind of see already that the drywall is looking different from the other materials, and certainly from the air in terms of that lag. So going a little bit further here, this is some data that we have from, this is about a year of data in 9 offices in Flagstaff, Arizona, San Diego, California, and Toronto. And what I did here is I calculated a time of wetness, so the amount of time that a parameter exceeds a threshold for both equilibrium relative humidity, which is the bar on the left, and relative humidity, which is the bar on the right. And I'm, to be efficient with time here, there are kind of 4 points I want to make about this data. The first point is the cities are very different from each other on bulk. So for example, Flagstaff, it's pretty dry, except they have a little monsoon season in the fall there. San Diego. Look at the differences between buildings and how extreme they are. So keep in mind the scale here, and I'll come back to that in a second. You have these buildings in fact, these offices, excuse me, that are in the same building, and they have these very different material parameters for the same material in each of the office. And then look at the difference between equilibrium relative humidity and relative humidity. And I circled the most extreme case here, but there is thousands of hours of difference between them, the time of wetness between them. So if you're just measuring relative humidity, you're not going to capture the full picture of moisture in these offices. And the final point I want to make about this picture is look at the overall scale on the y-axis. So those of you who know Scott Kelly, this S1W is his graduate student office. It's exceeding thresholds for time of wetness. We have to be a little bit careful because there's probably not a direct association between water activity and equilibrium relative humidity. But kind of ignoring that for a second, it's about half the year. It's exceeding some pretty high relative humidity thresholds on equilibrium relative humidity. So these are big numbers. So even small numbers represent, you know, hundreds of hours in some cases that things are staying wet. So to kind of finish up here, if you, in my opinion, if you want to understand the indoor microbiome, you have to understand moisture. And the depth at which you take measurements is really important. And I would advocate that we need to move towards more microbially relevant moisture measurements. And I'll finish by acknowledging some of my collaborators, students, and the funding source.